Imagine you're a merchant and you're selling some product by weight, and you need to know how much it weighs using a set of balance scales and some known weights. To use the balance scales, you put the weight on one side and you use the known weights on the other side until they balance. But being a merchant, you want to carry as fewer masses as possible. This is the problem I was trying to solve. What are the fewest weights you can have to measure every value up to n? Not knowing where to start, I began by taking a list of numbers n and factorizing them, and seeing what masses I can reach with just their factors. Obviously, for small numbers like 1 and 2, it's very easy to see that this is possible, and for larger prime numbers like 7, it's clearly impossible. The task is also going to be fairly easy for highly divisible numbers like 6 or 8. For a number like 8, with its factors of 8, 4, 2, and 1, and for trying to reach all numbers up to 8, we can see that 1 can be reached by simply using a 1, 2 can be reached by using a 2, 3 can be reached by using a 1 and a 2, 4 can be reached by using a 4, 5 can be reached by using a 4 and a 1, 6 can be reached by using a 4 and a 2, 7, 4, 2, 1, and 8 by using the 8 scale. If we fill in some zeros, we can see that this is actually just binary counting with weights. Using this system, for n weights, we can reach up to 2 to the n minus 1. Or, for 4, we can reach up to 15. That is using an 8, a 4, a 2, and a 1, all on the one side of the scales. For example, if we're trying to weigh something which weighs 13 grams, we can use an 8, a 4, and a 1, and our scales will balance. But is there a more efficient system that will let us reach higher numbers with fewer weights? When I was working through this full list of values of n, and using just their factors, I noticed something. For a value of 3, it's very easy to see how you can reach 3 or 1, but could you reach 2 grams? When I thought about this problem a bit more creatively, I realized that balance scales don't have to be used just with masses on one side. I could put 3 grams on this side, tipping the scales further that way, and use this 1 gram to balance it out. And here I guess we've shown that 3 equals 2 plus 1. Both sides of the scale are useful. As I worked higher and higher up the number line, I found this set of weights: 171, 57, 19, 9, 3, and 1. Using these weights, I could weigh every number up to 171. A surprising feat for only 6 weights. However, there are a few numbers that could be weighed a couple of different ways. For example, 70 could be reached using 57, 9, 3, and 1 to balance the scales. 70 could also be reached using 57 and 19, which weigh more than 70, but balancing it out using the 9 on this side of the scales and 1 to level it out perfectly. Given that 70 can be reached in 2 different ways using this scale set, means that it's not the most efficient possible use of the weights. There must be a more efficient use. One thing I noticed looking at higher and higher values of n is that a lot of them typically contained numbers like 1, 3, and 9. Using cubic numbers like 3 to the 0, 1, 3 to the 1, 3, 3 to the 2, 9, 3 to the 3, all the way up to 3 to the n. We could define a new counting system, one where each number can be used on the left side of the scales, the right side of the scales, or not on the scales at all, giving us 3 to the n possibilities. One of these possibilities is for no weights on the scale, 0, so we can only have 3 to the n minus 1. For half of these values, the weights will be on the right side of the scales will weigh more than those on the left, and so they won't count either. So total number of ways we can reach is 3 to the n minus 1 over 2. If we have a look at all the numbers that we can weigh using the set of weights made up of 9, 3, and 1, which should be 3 to the 3 minus 1 over 2, or 13. If we begin filling out this table of all the values up to 3 to the n minus 1 over 2, we can begin to develop a counting system. When we put a weight on the left-hand side of the scale, we use a 1. If we want to put a weight on the right-hand side of the scale, we use a negative 1. As we fill out the table, we'll see how the counting system works. To reach 2, we need to use the 3 on the left-hand side of the scale and the 1 on the right-hand side of the scale. To reach 3, we just need a 3. 4 is a 3 and a 1 on the left-hand side of the scale. As you can see, each time we reach 1 in one column, we index the next column and start counting from negative 1 again. So 1, 1 minus 1, 0, 1, index the next column, 1, minus 1 minus 1, 0, 1, index, 0, 1, index, all the way across until we reach 13, the highest possible number we can measure in this counting system, which should be 1, 9, 1, 3, and 1, 1, all on the left-hand side of the scales. What we've essentially invented here is ternary counting. In summary, using only n weights, we can reach every integer up to 3 to the n minus 1 over 2 by using a ternary counting system and both sides of the scale. So, if you ever find yourself as a merchant using only a set of balance scales, and you want to minimize the number of weights you carry with you, use weights of values 3 to the n.